Hello students, good morning, good evening and good night, depending on which time you are going to observe this lecture. Welcome to the 10th lecture on electrochemistry. Before going to understand today's topic on this lecture, let us first recap on what we had learned in different lectures, that is previous 9 lectures. In the first lecture we have understood the very preliminary concept of the electrochemistry. In that lecture we have discussed basically there is two parts in the electrochemistry. Number one part, that is the conversion of the chemical energy into the electrical energy. The second part, that is the electric energy to chemical energy. And in that lecture itself we have discussed about a very special simple cell, Daniel cell, that is the arrangement in which we understand the arrangement of the cells by which the chemical energy has been transformed into the electrical energy. In the second lecture we have discussed about the representation of the cell, how we can represent a galvanic cell or electrochemical cell. Also we have discussed in that lecture how we are able to calculate the cell potential, and also with the help of the standard hydrogen electrode how we can able to calculate the electropotentials. In the third lecture we have discussed about the electrochemical series, that I would say that is the backbone of the electrochemistry, that how with the help of this knowledge of the electrochemical series we can able to construct any type of galvanic cell which will help us for the transformation of chemical energy into the electrical energy. In the fourth lecture we have discussed about the Nernst equation, that is very much useful, that it enables us to calculate the cell potential from any type of concentration of the electrolytes in the cell. In the fifth lecture we have discussed some very essential relationships, like that is the relationship between the standard electropotential with the equilibrium constant, with the standard Gibbs energy change, Gibbs free energy change with your standard cell potential, and with the Gibbs energy and with the equilibrium constant. Three relationships that we have discussed in that lecture number 5. In the lecture number 6 we understood how this electrochemistry can be utilized for making different types of batteries, that is the primary batteries, secondary batteries and the other type of applications. And in the sixth lecture and 7th lecture we have discussed some very important terms to understand the electrolyte conductions by the ion, that is resistance, resistivity, conductance, conductivity. Also we have discussed about different types of substance in regard to its conductivity, that is conductors, non-conductors, semiconductors and the superconductors. In the 8th lecture we have discussed about different types of conductors, that is electrolytic conductors, or you can say that is metallic conductors, or the electrolytic conductors is not metallic conductors. Metallic conductors is the electronic conductors, and electrolyte conductors is ionic conductors, that we discussed. And also we have discussed how do we able to measure the resistance, or we can say conductivity of the ionic solutions with the help of the Wisdom's bridge. In that regard we have discussed about the conductivity itself. In the 10th lecture we have discussed about the molar conductivity and equivalent conductivity, and also we have discussed how the concentration of the electrolytes going to affect the conductance, the conductivity, molar conductivity, and all the things. And in this regard, we also discussed the Debye-Hackel-Unseder equations. So till time we have discussed this, and now in this lecture we are going to discuss another very important, that is the 10th lecture, that we are going to discuss the Kohlrausch equations, Kohlrausch law of independent migrations of ions. Kohlrausch law of independent migration of ion. Kohlrausch law of independent migration of ions. It is very, very important and very interesting. Let us understand. This is KK Mukherjee with the Science with Mukherjee YouTube channel. By using the extrapolation technique, extrapolation of the concentration to the zero, we can able to calculate, determine the limiting molar conductivity, that is a molar conductivity at the infinite solution, infinite dilutions, that we can able to calculate. But for the weak electrolytes, we cannot able to do so. In the weak electrolytes, what is going to happen when it is in an infinite dilution? At that time, there is a very fewer ions available, and the conductivity of the solutions will be very much difficult to measure. And in this regard, this law, that is the Kohlrausch law of independent migration of ions, which is going to help us. Kohlrausch, while investigating, while examining the limiting molar conductivity of the strong electrolytes, he found there is a very regular trend of the difference of the, that is, we can write, that is the difference of, he observed one very interesting thing, that the difference of the strong electrolytes, difference of molar conductivity at infinite dilution, molar conductivity. We found the molar conductivity, that is in the infinite dilution, of different strong electrolytes, and their difference is almost constant. So we can write this at 298 Kelvin, that is room temperature. We can write the difference of molar conductivity at the infinite dilution, that is gaseous, and this is initial. Its difference is same as the molar conductivity of, we can write KBr minus molar conductivity of NABr, and it is also be equated with this molar conductivity of Ki minus molar conductivity of NaR, and its value has been determined, that is 23.4 centimeter Siemens centimeter mole. This he observed that the difference of the molar conductivity, that is at the infinite dilutions of this strong electrolytes, is a fixed amount, fixed quantity, And from this he able to find out, able to initiate it, this law of independent migrations of ions. This is, he write that this law says, this law we can write, law says the molar conductivity at infinite dilution of the electrolyte solution. Here are the sum of molar conductivities of ions, sum of molar conductivity of ions. We know ion, there is basically two types, that is cation and anion. Multiplied by the number of cations and anions present in a formula unit, As for example, take example of this AXBY is an electrolyte. So we can write the molar conductivity at infinite dilution is of this electrolyte will be the sum of the number of ions produced, that is cations produced. This is a cation, A is the cation, B is the anion, and it is AX and BY. So when it will be dissociated, it will going to produce X number of cations. So we can write the molar conductivity of this cation A, its charge will be AY plus Y into molar conductivity anions. It will be Bx minus Y into Bx minus. So this is a general formula that we can see. Just for this electrolyte, we can write this. And take an example of a simple example that I was taking, that is of NaCl. So we can write this okay. So this is the law. Molar conductivity at infinite dilution of the electrolytes and the sum of molar conductivity of the ions, that is a cation and anions, multiplied by the number of the cations and anions present in the formula unit that we have seen. And for this example, we can use this. So this is a very, very important thing, and that comes from this regularity that what Kohlrausch has observed. And this law has a lot of application that we are going to understand. Now we are going to discuss the application of the Kohlrausch independent, this will be I in Kohlrausch law of independent migration of ions. What are the application? The first application you can see, that is to determine the molar conductivity. Determine, we can write in a very simple, that is molar conductivity of weak electrolytes. How we can do that? Let us understand. Weak electrolytes. Suppose we want to calculate the molar conductivity at infinite dilution of acetic acid. That can be applied by applying this law, Kohlrausch law of independent migration. If we know the molar conductivity infinite dilution of this sodium acetate, suppose we know this, because it can be easily calculated because it is a strong electrolyte, and if we know this, that is the HCl, and we know this NaCl. So we can able to calculate this. How we can do that? Let us understand in the simpler way. This molar conductivity of the sodium acetate at infinite dilutions, we can write this by applying the Kohlrausch law. Okay, then we can apply this. Okay, then we can apply for this initial now we can see this will be cancelled, this will be cancelled, and it will left with this. So it will left with this, and this is, you can see where we can equate with this molar conductivity of the acetic acid. In this way, we have to know the molar conductivity of the strong electrolytes, and by taking this, by summing it and then subtract it with the others that we have done here, we can able to calculate the molar conductivity of the electrolytes. Is the first application. Second application, we can do the degree of dissociation. Degree of dissociation, and that is represented by alpha. We know the weak electrolytes do not dissociate 100%. It will have dissociate depending on the electrolytes, sometimes it is 20% or the 30%. So what is the degree of dissociation of that acid or base? That also can be calculated by this, that is molar conductivity at concentration C and molar conductivity at infinite concentration, infinite dilution. At infinite dilution, so we can write this. So this will give the degree of dissociation. So determine the limiting molar conductivity of the weak electrolytes. We can apply the Kohlrausch law of independent migration of ions, and we also able to construct the degree of dissociation. That is the third application of this is degree of dissociation constant. Dissociation constant of weak acid and base, that we can able to calculate. For weak acid, we know this will be a dissociation reaction. For weak base, this will be the dissociation reaction. That we have already studied in the ionic equilibrium chapter. So there we know dissociation constant K or Kb. K for weak acid, Kb for the weak base. We can write this C alpha square by 1 minus alpha square. Alpha is degree of dissociation. So if we know the degree of dissociation, suppose it is alpha. Alpha is what? Lambda is the ratio of this molar conductivities, that is at the molar conductivity at the concentration C and molar conductivity at infinite dilutions, and if we put this, we will get C into A lambda m by 0 the whole square divided by 1 by lambda m by lambda 0 the whole square, lambda 0. This is not square, this is lambda. This is lambda. So from this we can able to calculate, it will be C into A. So this will be this. Okay. Now again, another thing that we can able to understand, that solubility of sparingly soluble salt. Soluble salt, that is also be calculated, where lambda m is equal to lambda m infinity, because it is saturated and it is at the infinite dilution. So we can write this, and molarity is solubility. We can write this, molarity is equal to solubility. So we know lambda m is equal to conductivity kappa into 1000 divided by molarity. So we can write this, molarity is solubility. So we can write this, solubility is equal to, we can write K into 1000 divided by lambda m at infinite dilutions. This will give the solubility. When we know the solubility, we can able to calculate the solubility product also. So these are basically the applications of the Kohlrausch law, and it is very important law. Different type of numericals is going to come from this law. So that is all for today's lecture. In this lecture we have discussed about the very important thing. First we have discussed in the previous ninth lecture what we have discussed. In this lecture number 10 we have discussed about the Kohlrausch independent migrations of ions law, how he initiated this law, and how this law is helpful for different applications by it is going to determine the molar conductivity of the weak electrolytes at the infinite dilutions. Second, the degree of dissociation constant of weak acid and weak base, and also solubility product for the sparingly soluble salt that can be applied by using this law. So that is all for today's lecture. If you like this lecture, you can share to your friends. Thank you very much for watching.